Okay, so sorry for going a bit over time yesterday. Feel free today to remind me if you see that I'm going over time. Just raise your hand or shout or complain. So let me first remind you very briefly what we did yesterday, and today we will go into. We will start looking at how to derive generalization bounds, and basically what are the main ingredients of these bounds, and what are the techniques, the classical techniques to obtain these bounds. Okay, so yesterday we talked about this notion of consistency, which was essentially the fact that you take an algorithm, you sample data from a distribution, and as you get more and more data, the error of this algorithm will converge to the best possible error under that distribution, right? And we showed that obtaining such consistent algorithm is very easy in the countable case, and it's actually trivial, so it does not really give us anything in a way. And in the continuous case, it's not much harder. It's just a matter of averaging in a small cell and making sure that the size of the cell decreases to 0, but not too fast. And then we say that you can easily create distributions for which any algorithm, no matter what it is, can just have a bad behavior, right? I mean, it may eventually converge to the best error, so it may be consistent, but still that does not help you much because on finite sample, its performance can be arbitrarily bad. Okay, so essentially the conclusion is that to get any more interesting results, we either have to restrict our objective. So instead of looking at all possible distribution, just look at a small set of specific distribution, and then we may hope to prove kind of more specific results, or we have to find some other way. And that's what we will do today. So, by the way, I put the slides from yesterday's lecture on the wiki now, and I will put these ones today. So here's the notation. Maybe I should write it down so that we always have it with us. So basically, we consider some input space X that can be arbitrary. The output space, we will... Yes? Oh. So which part do they see? Did they see a part of it? Or? Okay, well, then let's do without it. Okay. Okay. Yeah, they can complain, right? Okay, at least I will keep the slides up for a while I'm writing that, and then hopefully they can take some notes or something. And we consider instances which are pairs of x and y, where x belongs to x and y belongs to 0, 1, right? And we get to see n such instances. So n is a sample size. So we have x1, y1 to xn, yn. And they are all sampled independently and identically from the distribution P, which is unknown to us, right? And we have a predictor, G, that is a function from x to y. And for any prediction of that predictor, we penalize it with a loss function, which in this case is just the indicator. So it's 1 whenever g of x is not equal to y. Whenever we make a mistake, we pay 1, and otherwise we don't pay anything. And the relevant quantity in our case is what we call the expected error. So the expected value of this quantity under this distribution P, right? Which we can also write, because this is either 0 or 1, we can also write this as directly the probability that g of x different from y. Okay? And two other useful things. One is Gn, which is what is created from these, the function that we create after having seen all these n instances. And G star is our target optimal predictor, which is the one that minimizes so the arg min, where the arg min here is taken over all measurable function of the loss of G. So all measurable functions G. So the function that minimizes this error is called G star. I mean, it may not be unique, but it doesn't matter because we're not interested in the actual values of that function, but the loss corresponding to that function. So the loss is unique. The value of the loss is unique. Okay. Yes. 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 Sure. Yeah. So, okay. So when we say, I mean, Gn going to G star is actually L of Gn going to L of G star that we are interested in, right? And of course, this depends on the sequence of data that we get, which is a random sequence, right? So what we are interested in is convergence in probability, for example. So something like the probability that something like this, larger than epsilon, has to go to 0. So that would be weak convergence or strong convergence, meaning convergence, how is it called? I've got a name. Wow. So the probability that this goes to 0 equals 1. That's the strong convergence. But it is convergence in probability for these random sequences. Okay. Okay, keep that here. Okay, so remember that the problem with this North-Friedland theorem is that if we consider this quantity L of Gn minus L of G star, we can construct distribution for which this is large, no matter what the algorithm is. So this is a bit annoying. So what can we do? So as I said before, one thing we can do is to restrict the set of probability distributions, this P. If we take it in a restricted set, and we prevent these bad cases that were created for the North-Friedland theorem, then we may hope to get, to be able to upper bound these by some quantity that goes to 0 at a certain rate, and so on. But as I said before, we would like to avoid these assumptions as much as possible. So what we can do is maybe try to find another quantity on the basis of which we can really compare two algorithms. So the idea is to do the following decomposition. We look at this difference and we express it into two terms, the sum of two terms, by introducing not a class of distribution, but here a class of functions. So I'm introducing this curly G here, and let's consider this is a class of interesting functions like, I don't know, linear classifiers or classifiers based on polynomials or whatever, something that you are interested in. Okay, and we consider the best such classifier in this class. And we write this error by decomposing it into the difference between the loss of our algorithm minus the loss of the best such classifier, and this extra term which corresponds to how bad or how worse is the best in this class compared to the best overall. And so this term here is often referred to as approximation error. It tells you with this class of, say, linear classifier, how well you can approximate the target function, the optimal function. So this is the best you can do within this class, curly G. Okay? And the important point here is that it's a deterministic quantity. So this does not depend on the data, right? It does depend on the distribution P, but it does not depend on the actual instances that we have seen, x1 to xn. Okay? So, and the problem is to estimate it or to know how much this quantity is, we need to know what is this distribution P. So if we don't know about P, we can't do anything about this quantity. So maybe that's not the interesting part of the decomposition. And a more interesting part of the decomposition is the other part, which we call the estimation error. So there are many ways we can write it. So it's the difference between the loss of algorithm and the loss of the best. We can either write it, L of Gn minus the mean over G of L of G, or the max of the difference. We can either put the mean here or put it outside, and the mean becomes a max because there is a minus sign. So we can write it the max of this difference, L of Gn minus L of G, max taken over all this class of classifiers. So, I mean, we may call that, it's not very standard to call it this way, but I like to use this term, the maximum regret. So this is how much we are unhappy about not having been able to match the performance of the best in the class. Yes? No. Yeah, now G is a variable, right, that is maximized over. Important point is that is a random quantity because it depends on the data via Gn, right? Gn may fluctuate. I mean, for any different training sample, you get a different Gn, so this quantity will vary. And now what is important or interesting is that this quantity can now be quantified without any assumptions. So we can have upper bounds on this quantity that do not depend on the distribution, so that are valid for any possible distribution as long as this class is relatively small, let's say. Of course, if we just take the class of all possible functions, we are back to our LG star, and we know that we can't do much. So the idea is we want to focus on this estimation error, make as few assumptions as possible, because we know that theory, as I said in the very beginning, theory will not be able to justify our assumptions, but we hope that the theory will be able to tell you, what is best within this set of assumptions. If we compare to this set of classifier, like linear classifier, what best can we do? And independent on the way the data is distributed. So, how do we get these bounds? There are three ingredients that I will give you details about in the following hour. One is called the fundamental inequalities. So they allow to relate whatever we consider as a quantity, this L of Gn minus L of G sub G. They relate that to what we call empirical processes. I will tell you what that is in a moment. Then the second step is to look at the deviations of these empirical processes, and this can be done with a quantitative version of the law of large numbers. And then we have to kind of glue all the elements together, and that will be done by the union bound. So, first of all, I have to explain you the kind of bounds that we are aiming at. I told you that this quantity that we are trying to upper bound or lower bound is a random quantity. So it means it doesn't have just one value, but it has one value for each realization of the training set. So there are two ways in which we can kind of try to circumvent this problem. One is by looking at the expected value of this quantity, right? Expectation now here is taken over all possible training sets. Remember that within this L, there is already an expectation, right? Because capital L is the expectation of the loss when you sample these test points on which you are measuring the loss. So this expectation is with respect to xy, the test point. And then we put an additional expectation here, which is with respect to the sampling of the data x1, y1 to xn, yn. Okay? The other way is to look at not expected value, but the tail probabilities. Because it might be the expectation is small, but sometimes the value is large. So we want to have some kind of guarantee that the value will not be beyond a certain threshold, let's say. So what we're interested in is the probability that this quantity goes above a certain value epsilon. And if we get an upper bound on that, if we say, oh, this probability is smaller than something, then it will guarantee us that, with this much probability, we are sure that this is, with 1 minus this probability, we are sure that this is lower than epsilon, for example. Okay, and of course, if we can get upper bounds for this quantity for any value of epsilon, then we can actually get upper bounds on the expectation. Because this is richer, we have we can see all the behavior of this random variable. And we can recover the whole distribution in a way. Just a note, and that will connect to tomorrow's lecture, Nicolo's lecture. We can, in the case where instead of putting the expected value here, we take the cumulative error that I mentioned in a slide in yesterday's lecture, which is basically the sum over the training data of the errors. You can even look at the maximum over all possible sequences of this quantity and also get upper bound. But for now, we will focus on this part, the tail probabilities. So, first ingredients, fundamental inequalities. We want to upper bound this quantity by something that we know how to control. The idea is to introduce what is called the empirical estimate of the loss. So this loss, this expected value of the loss, we cannot measure it. So let's try to replace it by something that we can measure. And the natural replacement is the corresponding value measured on the data points, right, on the training data. And this we will do for a specific algorithm. So what is the empirical loss? We call that the loss, the expected loss is written like this. What we do is we just take the empirical average, we sum over the data, take the loss, and scale it by 1 over n. And this is perfectly natural to do, and turns out that it's easy to prove that if you take the expected value of this quantity over the sampling of the data, so over the training sets, then it's actually the expected loss. So this quantity here is called an unbiased estimator of the expected loss. But now that's where things get a bit more subtle. This is true when G is fixed. What we'll be interested in is not L of G for an arbitrary fixed G. It's for a G, this Gn that actually depends on the... And that's where things get a bit complicated. Okay, so let's take a specific Gn that will kind of make the calculation easier. And a natural one, again, one that you probably have heard of before, is this empirical risk minimizer. Or in this case, I call these things losses, so maybe we should call empirical loss minimizer. So we consider a class, G, which, in our case, we can take as the same as this G we are comparing our performance to, let's say. So this, let's say, it's again the class linear classifier, let's say. And we're taking the function in that class that minimizes not the expected loss, but the empirical loss, because that's the only thing that we can measure. Okay? And, well, if we look at the loss of this Gn minus the best loss in the class, it's easy to see that this is no more than twice the supremum of the difference between the loss and the empirical loss of the same function of some G. Okay? So to prove it, you just write L of Gn as L of Gn minus Ln of Gn, empirical, plus Ln of Gn. Now you use the fact that Ln of Gn is lower than Ln of any G in the class because of this. So you replace this Ln of Gn by Ln of G for an arbitrary G. And then you then get ln of g minus L of g, which again gives you something like this, right? Is it clear? You can write it down if you are not confident. Okay, so now what we have done here is to replace a quantity that we had initially in mind by something that actually is comparing the expected loss with the empirical loss. And we recall that the empirical loss is an unbiased estimator of this quantity. So, we may expect that these two things are relatively close in general. So we may expect to have this go to 0 eventually when n goes to infinity. Well, we have to still deal with this supremum, and that's the difficult part, but I'll show you how to do that. And of course, you can also, if you're interested in expectation bounds, you can write the same thing for the expectation and work this out. Yes?
You really need the absolute value.
Yes, because you have L minus Ln and then Ln minus L. So they are not in the same direction. So if you, you could have a sum of two terms, one which is L minus Ln and the other one which is Ln minus L. It depends. This is the kind of easiest way to do, but you can also decompose it because sometimes you have a better control on the, one-sided deviation. These are called the two-sided deviations. That was for the empirical risk minimizer for any arbitrary algorithm. So if Gn is in some class G, you can also try to write the same thing, but you have extra terms because now you can no longer use the fact that Gn is the empirical risk minimizer to replace this Gn by G. And essentially, so you can do the same trick of introducing Ln, and you basically obtain something like this, but now you no longer can get rid of this difference. You can only get rid of this one because the loss is non-negative, and you still have this one. So it's not as nice, and in particular, it's not very interesting because, so if you remove this term, you only have that, and the empirical loss of your classifier may not go to 0. So you may have a bound that doesn't go to 0 when n becomes large, while still this quantity may go to 0. So it's really not interesting bound. It's sometimes used to provide bounds of this form, where you compare the true loss of your algorithm with the empirical loss of this algorithm, and you have some extra term. So when you are interested in this difference, and you don't want to relate to the best in the class, for example, then this technique can work. But that's not where we'll be looking at. So for this absolute value thing, you can indeed have a refined version where you only have the deviations in each direction, and you only take the supremum in one of them. And here, because this is a fixed function, you don't need to take a supremum. You can only look at the deviations for this specific fixed function. But again, we will not really look at the details. So now what I'll do is give you some, a bit of formulas about probability. If you just to remind you some basic facts about probability that we will use later on. So the union of two events. So that's a basic property, or even an axiom of probability, that probability is subadditive. So if you take the union of two things, the probability that these two things, this union occurs, is less than the sum of the individual probabilities. That's, again, you can derive that from the axiom. If some event implies another one, then the probability of this first event is less than the other one. Another thing that is useful is this inversion. So if we have a tail bound, so if we can prove that the probability that x is larger than t is less than some f of t, then we can also rewrite this as, with high probability at least 1 minus delta, or some delta, x will be less than the inverse. Well, I mean, you just have to write f of t equals delta to set f of t equals delta, and then you inverse this quantity, and you get x is less than nth inverse of delta. Right? So, I mean, it's sometimes convenient to go from this notation to this notation. When I told you that you can recover the expectation bounds from the tail bounds, this is how you do it. You just integrate the tail bound, and that gives you the expectation, at least for non-negative random variables. Another convenient thing, we will not use it explicitly, but that's useful to know. Jensen's inequality, if you have a convex function, you can actually take it inside the expectation and get an upper bound. Markov inequality, that's also very classical. For non-negative random variable, you can bound the tail by expectation divided by t. A slightly refined version for arbitrary random variable, if you look at the deviations to the expectation, you can bound this by the variance divided by t squared. Chernoff is some sort of generalization of that. So for all random variables and all t, you can bound the tail by this quantity. You take the exponential with some parameter lambda, and you can take the infimum over all non-negative lambdas. And these are very convenient tools when you want to get upper bounds on tail probabilities. Okay. Now I will introduce a little bit more of notation, but with the hope of making things simpler, and I hope I will not confuse you with that. Instead of writing always x and y, I will just consider this as one single random variable that I call z, and the xi, yi will be called zi, and xy will be called z. And now, instead of looking at functions g from x to y, I will look at functions that apply directly to this pair. So I define a function f that takes a pair x and y, and that computes the error of a corresponding function g on this xy. Okay? So instead of writing indicator of gx different from y, I will just write f of z. Right? So for each g, there will be a corresponding f. It's just a matter of notation. There is nothing really subtle here. And again, to simplify, instead of writing expected value of f, x, y, or f of z, I will write just pf, and the corresponding empirical pnf. Okay? So, as I said before, what we are interested in is the deviation between the expected and the empirical. That would be just written pf minus pnf. And yeah, I will kind of go back and forth between this g and this f. So for each function in g, there is a corresponding loss function in f. And for each function in f, there is a corresponding classifier in g. So what is an empirical process? I told you about this notion of empirical process. An empirical process is just this. So what does it mean? This is a collection, right, indexed by this class f. It's a collection of random variables. So each pf minus pnf is a random variable that depends on the training sample, right? And which corresponds to a given f. And I have many of them. Like for each function in my class, so for each linear classifier, I have a corresponding f here. And for each such f, I have a random variable which describes the deviation of the empirical error to the true error for this specific classifier. So that's just what it is. So why do we call that empirical? I mean, you've heard about Gaussian processes before. It's just the same. So a Gaussian process is a collection of Gaussian random variables. And an empirical process is a collection of empirical random variables. Empirical meaning that they have this very specific distribution of being the difference between an expected value and an empirical expectation. And it turns out that there are many techniques that exist for bounding the very thing that we are interested in, which is not one single deviation, but the supremum of the deviations over the entire class. So let's look at now how to get to these deviation bounds, like how to prove things about these empirical processes. The first thing is this, the first thing that you may have heard of before is this law of large numbers that essentially tells you that if you look at the difference between the expectation of something minus the empirical average, so you measure it for n instances and you take the average, then this difference goes to 0 with probability 1. So this quantity strongly converges to 0 in probability. In the limit. Okay. So at least what we have now is it's kind of I told you that the expected value of this is this, but now it's an even stronger statement. I'm telling you that when the sample size increases, those two things will become closer and closer. Okay? But the question is how much or how fast this will happen. Because this is, just this will only allow us to prove consistency again, right? And actually this is the kind of thing that is used in the consistency when you want to prove that the average in a certain small cell converges to the expected value. So it does not bias much. So what we want is really to be able to say how fast this happens. So for that there is a very nice tool which is called hovdings inequality. And hovdings inequality actually can be derived using this Chernoff trick that I shown before. It's more or less a direct consequence of Chernoff and a little bit of cooking up or massaging the exponentials. And this is really the most straightforward version, quantitative version of the law of large numbers. So basically it will tell you that if you have random variables and if your f of z is bounded, so if you have bounded random variables basically between a certain interval a, b, then the deviations between the true and empirical will be bounded as follows. So you have so this characteristic Gaussian tail, right? So it's exponential to the minus epsilon squared divided by some quantity which is reminiscent of a variance. And so basically it will tell you that this will decrease very fast. You have a sharp decrease of the size of this quantity when epsilon increases. And when n increases, you also have very exponentially fast decay. Okay? So this is all good news. We know that our quantity not only will converge to 0, but it will converge probably reasonably fast. So let's use this inversion trick to rewrite it in a more understandable way. So we just set the right-hand side to be equal to delta, right? And we try to express now epsilon as a function of delta, which is this function here. So basically we prove that the deviation larger than this is less than, the probability that the deviation is larger than this is less than delta. So now if we take for delta a small value, then we know that at least with probability 1 minus delta, so with, say, 99% probability, if we take delta to be 1%, we are guaranteed to have this. So this is important. This means that if we take training samples and we repeatedly take new training samples of size n, for 99% of these training samples, this bound will hold. And for 1%, it may not hold. So maybe this will be larger than that. Okay? So this is why we say with high probability or high confidence, this bound will be true. So this is, when you're not used to this, it takes some time to understand what really it means. It doesn't mean, right, it's different from a deterministic statement where you know that A is less than B for all the cases. Here, we know that A less than B most of the time, but sometimes it may not be. Okay? But it gives us a good idea of how this quantity behaves, and when n increases, basically it tells us that the deviation will be of order 1 over square root of n, so it may decrease gracefully towards 0. Okay? Clear? So we already have made a good step. And one immediate consequence of this inequality, if we apply it directly to this f function, which is the loss function, is that we can prove that with high probability again, the expected value of the loss is less than the empirical loss of a given classifier plus something like 1 over square root of n. So this is something useful to have in mind. Keep in mind that for any fixed function that you pick in your class, this function should not depend on the training data. Otherwise, this bound doesn't hold. But you have a fixed function that you observe. You keep sampling training sets. So most of the time, the expected loss of this function will be not more than the empirical loss that you measure on your training data plus 1 over square root of n. Yes? Yes. So the question is, what does it mean that G should not depend on the data? Because when you're doing learning, G depends on the data. Yes. So this statement here is like, if you keep sampling training sets, and every time that you sample a training set, you have a different function G, then this statement does not apply. And the reason is that what we said before is that this is true for any random variable, but our random variable here should be of the form of this one. If we look at L of Gn, right, or Ln of Gn, so if we look at a classification function that depends on the data, then we cannot write it as a sum of independent random variables, because, I mean, it will be clear in a minute because I have some other explanation, but just, so Ln of Gn, right, this is indeed a sum, but it's the sum of some indicator function of Gn of xi different from yi, right? And the problem is that for hovdings inequality to hold, you need to have a sum of independent random variables. Gn of x1, let's say Gn of x1 different from y1 depends not only of x1, but also on all the other xn via Gn, because Gn depends on all of them. So this is really not a sum of independent random variables, because all the examples are used to compute any term in this sum. That's what we'll see in a moment. That's exactly the point, actually. How to go from this, which tells me something about a given function, to something that tells me the same thing for a function that depends on the data. Okay, so as I said, we have to consider a fixed function, right? And this does not apply when the function depends on the data. So how do we do? Let's try to understand why this is the case and why when the function depends on the data, we have a problem. So basically, we have the fact that for each fixed function, so we look, let's say, at several linear classifier, one which is vertical, one which is horizontal, say in 2D or something like that. So we have a couple of them. So for each of them, we know that if we keep sampling data, we will have that most of the time. So for at least a fraction 1 minus delta of these training samples. But the thing is, the cases where this is true will differ for every, so maybe for, let's say we take 100 training samples. So for the first classifier, for the first 99 training samples, this will be true, but for the last one, it will be wrong. Now we look at the second classifier. For the last 99 training sample, this is true, but for the first one, it's not true. So what I'm trying to say is that for each given classifier, the set of events on which this is violated will be different. And it may be that, on each such set, each training sample, there is at least one classifier for which this is not valid. So that's why we can't really say that this is valid for all classifiers simultaneously and and hence for all classifiers that depends on the data. Because for the observed sample, we may have just picked the one function for which this was not valid for the corresponding training sample. There may be this problem that occurs. Again, I will rewrite this in a slightly different way to make you understand better. Here's the problem. If we look at this difference, PF minus PNF, or the true minus the empirical, if we have a large class of function, we can always choose a function in this class. Let's say we have the class of all functions, just to simplify. We can find a function which is 0, which correctly classifies all the training data, but incorrectly classifies all the other data points. So in this case, we will have this value equal to 1. So does this contradict what we said before? Well, for this fixed function, we have, and for this fixed training set, this value is 1. But if we keep sampling training sets, then the difference between true and empirical for this given function will still be close to 0. So basically, if we construct the function after seeing the training sets, so let's say this is Rx, right? So let's say we sample a training set which is like this. We can create a function which is 0 at all data points, but then 1 everywhere else, right? So for this function and this training set, the difference is 1. But now if we fix the function and sample other data points, let's say here, because the kind of expected value of this function is 1, and the empirical now on these points is 1, then the difference is 0. So for most training sets, the difference will be 0, and just for one single training set, the difference will be 1. Okay? So this function in itself does not violate the theorem, but it's just that if you pick this function after seeing the data, the data, then you violate the theorem. So it does not contradict hovdings inequality, but it shows that hovdings inequality is not enough to get what we are looking for. Yet another way to see this phenomenon, which is really the most fundamental phenomenon in learning theory. Hopefully this will not confuse you, but gives you some different points of view on this same problem. Let's look at the different graphic, where here in the horizontal axis we have the functions. Let's assume each point in this axis corresponds to one function, right, in our class. And this quantifies the loss, the expected loss of our functions, or expected or empirical. So we plot here. Sorry, the notations are different from what I have in the slide. So basically, this curve here is the expected loss of our functions in our class, right? So for each function, there is a corresponding expected loss, which is a fixed value. So this curve is deterministic, right? It's fixed. And now, if we take a sample and we measure the empirical loss of each function, we get 1 point on this curve. So these are all the empirical errors of this function in the class. And of course, this curve will not be the same as this one because there is some bias in the training data. There is some difference in what we observe in training and what we observe on average. And we know that if we look at the fixed function here, the difference between those two curves will be fluctuating, right? This empirical curve will fluctuate, but the deviations at this point will not be larger than 1 over square root of n, and when n goes to, when n increases, then these two curves will become closer and closer, right? So that's true for one fixed function. But because we have so many functions, and we may be able to find some points along this axis where the difference is unreasonably big, let's say. Because for these specific training samples, there might be cases for which the bound that we had before, this 1 over square root of n bound, is violated. This is allowed by hovding. Hovding allows each function sometimes to violate this bound. So if we have enough functions here, and we look at enough deviations, we may find one that is very big. And especially if, like in the case that we had before, if we look at all possible functions on this axis, then we may find a function for which this difference is actually equal to 1 for any given training sample. So somewhere, so these curves, they will keep, the empirical curve will fluctuate around the true curve as we take training samples, training sets. And we know that if we look at a given point, the fluctuation will not be that big. But if we keep looking further and further in the set of functions, we might find some place where the deviation is big. So there will always be some place where the deviation is big, but this place will occur rarely if we look just once at one point. Okay, is this a bit clearer? So this is really what's happening, and the bigger the set, the more likely it is that we can find big deviations. So if we happen to have picked exactly this function that has the big deviation, then we violate the hovdings inequality. Okay, so that's where we need this third ingredient for the bounds, this union bound, that will allow us to patch together many different hovdings inequalities. So, okay, let's consider the case of two functions. And let's look at Ci being the set of training data for which hovding is violated. Right? For given epsilon, the difference between true and empirical is larger than epsilon. So for, we have F1, F2, and for each Fi, we define this set Ci. So we look at the set of training samples for which hovding is violated for each function. So what we know is that the mass of this set, right, the probability of this set is less than delta for I equals 1 or I equals 2, right? That's what hovdings tells us. Now what we want to have is we want to know when those two things are violated. So we want to know when either of those are violated, right? So we look at the union between C1 and C2 and remember this basic fact that the probability of the union is less than the sum of the probabilities. So if we work this out, and we can even generalize trivially to n functions, we get that the probability that for one of the functions hovding is violated is less than the sum of the probabilities that hovding is violated for one function, right? So we can read this as in the following way: the probability that there exists a function in this set from F1 to Fn for which this is violated, so this is larger than epsilon, is less than the sum of the individual probabilities, which we know are of this form. So I forgot this b minus a that was in the hovding case because now a and b are 0, 1, right? If I'm restricting myself to the binary case. So I basically have n times, so capital N here is the number of functions I'm considering, capital N times the deviation. So what does this tell me? This tells me that if I look at the bad cases and I kind of I accumulate them, right? For a given set of functions, I say, well, for this function, I have these bad cases. For this function, these bad cases. For this function, these bad cases. Now I take all of them because if I take all of them, that I'm guaranteed that at least one, they are bad for at least one function. Then I get this deviation. And if I invert the statement, then I will know which are the cases for which everything is fine. So for which all the hovdings inequalities simultaneously are valid, right? So if I do that, I get this statement. Now, if I have a set of n, capital N functions, then I know that with large probability, the deviations for any function in that set will be less than this quantity. I have this extra log n factor which comes from inverting this bound, right? When I invert and I try to express epsilon in function of delta, I take the log, so this gives me this log n factor. So basically I see that compared to the deviation I had for one function, the only extra term that I get is this log n factor here. But I still have this nice 1 over square root of n behavior. So now this is valid simultaneously for all functions in a given set. And you see again this phenomenon that if you take a large set, you get less and less control. So if capital N increases, at some point this will become void, like this will become larger than 1 and useless, right? So this is only useful if n is not too large, or I mean the ratio of log capital N divided by small n is not too large. Another thing to note is that there is this nice coding interpretation where you can interpret the log of capital N as the number of bits required to encode one element of this class G. So this tells us that, you know, the kind of size of the deviations depend on how many bits are required to encode your functions in your class. So it's kind of a nice way to measure the size of your class as number of bits it takes to encode it. But this is just a remark. Okay, and well, I mean, so is this clear how we went from hovding for one specific function to a generalized version of hovding using the union bound for n functions simultaneously? So in particular, of course, this then applies to, I mean, we can plug Gn here if our Gn is picked within this set of n classifiers. Right? So this will apply to the empirical risk minimizer in that class, in this finite class. We'll see how to go to infinite class later on, but for a finite class, now we have a statement that, I mean, we can apply this to our Gn. Okay? And I guess now it's a good time to stop. Thank you. So we can start in 10 minutes, I guess, or maybe 15 minutes.